Okay, so here we got two slits separated by S, and we've got this distance D, which is the distance from the source to the screen in a perpendicular direction like that. So what we're going to do is focus on the possibility of a bright fringe being formed. In other words, of there being constructive interference between the light which has travelled from this source and has travelled from this source. And we saw by looking at the wavefront picture that we had in the earlier part of the introduction, that the difference in path length, which is going to be this, so if we draw a line perpendicular to this ray like that, so that is a triangle, so that is a 90-degree angle there. This distance here we saw had to be a whole number of wavelengths in order for when these two rays finally meet. And remember, we've drawn them parallel only because they're so close to parallel that it makes no difference on this scale, because really they're going to be meeting all the way over there somewhere, so that they're you know, when you just look at this end of it, you can't see the deviation from parallel, but they are eventually going to meet at the same point over there. So the only difference in path length is that there, and we saw that that had to be equal to a whole number of wavelengths in order for you to get constructive interference. So we can set that distance and say, right, to get a bright fringe, that distance has got to be equal to n lambda. If this angle is theta, so that's the angle between the ray of light coming through here, the diffracted ray, and the normal, the perpendicular line like that, then you can see just by considering triangles that that angle must be 90 minus theta, and therefore, because this is a right angle triangle, this is also theta. Okay, so just by thinking about the properties of triangles, you can see that that angle is the same as this one, is theta, and therefore you can see that there's this triangle gives us a very simple trigonometric relationship, which is that n lambda, this distance here, so this indicates that n lambda, that distance along there, is equal to the length of the hypotenuse, which is s, because that's this distance here, multiplied by sine theta. Okay, so that's going to be a requirement for getting constructive interference, that the difference in path length has to be a whole number of wavelengths, and that leads us to this relationship that you're going to get constructive interference when you get that angle, those particular angles theta, such that n lambda is equal to that distance s times sine of theta. But that's not actually the relationship we normally use. You probably can see that's very similar to the diffraction grating relationship, which we'll come on to, but that's not the relationship we normally use with the double slits. And in order to see where that comes from, we need to look on the sort of bigger scale at what happens all the way when these rays finally have converged, so that we take the full distance d into account. So here we've just been focusing on what's going on right near the source, and as we said, because this depended on this parallel lines thing, the actual screen on this scale is going to be way over here, so that you don't notice the convergence on this very small scale here. What we're going to do now is switch then to look at a scale where we do actually bring the screen in as well. So if we draw a picture like this, we're just going to focus on one of the slits here, and basically this, we're going to cheat a little bit with this bit of the derivation, because doing it a bit more rigorously is kind of messy. So what we know is, well, actually, let's put them both in to start with. What we know is that if we had in-phase waves emerging from these two sources, that we would get a central fringe there focused on the midpoint of that line, and then we would get fringes spread out to either side of it with a spacing which depends on the separation between the screen and the slits. So we could move the screen to and fro until we arrived at a situation where the next fringe was exactly here. Okay, so this is the central bright fringe, and this is the next one. Okay, so we're gonna cheat a little bit on this part of the derivation because doing it more formally is a bit messy. But we know that the spacing of the fringes on this screen is going to get wider as you move the screen further away. I mean, common sense just tells you that if you know, as the angle increases, as they diverge, they're going to get further apart on this screen. So clearly you can see it would be possible to move the screen to a distance where you had this situation. So we know that if the waves are in phase as they emerge from the source here, that we're going to get a central bright fringe which is going to be here. So this is a bright fringe right in the middle here. And it would be possible to move the screen to such a distance that the next bright fringe came there, and obviously there as well. So in other words, that it just happened to be in line with the slit, and that would only happen at a particular distance d. But if we just work out our relationship for that particular distance, it then turns out that it will be valid for all distances, but it's just easier to do the sort of maths for this one. So we've got these bright fringes there, and we know that we're interested in this parameter w, which is the separation between adjacent bright fringes. So that's w, and so is that. Okay, so if we're looking to establish a relationship between what we can see on these two scales, we can do that using this angle theta, because this is the angle which the diffracted light has to make in order to, we decided, produce constructive interference on the screen. And that's what we've done here. So this angle we can mark on like this. Okay, so if we draw a line headed up there and extend it to here, okay, then we know that that angle is going to be theta. Okay, so we've got a connection between the two there. So we've got W, and we've got D, and we've got theta. Now you can see that what trigonometry tells you is that W divided by D is equal to the tangent of theta. However, what you can also see is that provided theta is a very small angle, that the length of this line here, the diagonal one that goes from there to there, is only very, very marginally different from D. So for example, if theta is 5 degrees, then cosine of 5 degrees is 0.996, which means that D divided by that length is 0.996, so they're actually very close to being identical. So to a reasonable approximation, to a good approximation, we can say that this length is near as damn it d. And so we can write down that sine theta, the sine of that angle, which is opposite over hypotenuse, is approximately equal to w over d. Okay, so that looks weird because you think now that should be the tangent, but as I say, what we're doing there is just saying that this length here is so close to being equal to d that we can write that relationship as being approximately true. So now we have two relationships involving sine theta. So if we take this one and rearrange it to move the s over there, we get n lambda over s is equal to sine theta. So let's take this one across to here. So we've got n lambda over s is equal to sine theta. But remember that the way we were thinking about it here, we were thinking about the difference between the central peak and the next one. In other words, between two adjacent fringes. And so the difference in path length is just one wavelength if they're adjacent bright fringes. And so n is 1. So we can say for adjacent fringes, that lambda over s is equal to sine theta. And from this one, we can say that sine theta is also equal to w over d. And so obviously we can combine those things and say that lambda over s is equal to w over d, which means that w is equal to lambda d over s. And that's the standard relationship that is used to calculate the fringe spacing depending on the experimental setup, so the wavelength of the light, the distance between the screen and the sources, and the separation of the slits. So that's a very important equation which is on your data sheet. And okay, our derivation of it has been sailing slightly close to the wind, but you can see the origin of it there hopefully fairly clearly